Hey guys, just going to run through question 3.3 from the tutorial. So in the question, they've given you two joints with different lengths, 5 meters and 27 meters, and they've given you the normal stress at each of these joints. A little bit of information here, and we're going to use that to plot it. First question is, draw the shear strength envelope over a range of normal stress values. So basically they're asking us to plot this data, and we're going to have to fill in the gaps between that. We know what those gaps are. The second part of the question, they tell us about plus or minus 400 kPa, plus or minus 3 MPa about each of the normal stresses. So, the small sliding mass, we have 1.4 MPa plus or minus 400 kPa, that gives us 1 and 1.8. For the large sliding mass, we've got 23 MPa plus or minus 3, gives us 20 and 26. We use the Barton equation to find out what the shear stresses are corresponding to these normal stresses. So if you do that for each of them, as I've done here, you get the corresponding shear stress for all of those. Once you've done that, you can plot it. I plotted it in Excel. Looks something like that. There's the equation of the line. So that's the first part done. Second part of the question, estimate shear strength parameters, friction and cohesion, so that's like the Coulomb parameters, by drawing tangent to the curve at each of the normal stresses. I'm not really sure what it means by draw a tangent curve, but you can solve it simultaneously just from Coulomb's equation. So here's Mo Coulomb equation. If we plug in our numbers from the previous part, so over here, for say 1 megapascal normal stress, we have 1.9 shear stress. The 1.8 normal stress, we have 2.9 shear stress. So we plug those two numbers into the Coulomb equation. We get those two equations, solve them simultaneously as I've done, and you end up getting 650 kPa for your cohesion and 51.34 for your friction angle. Do the same thing again for the large sliding mass, so that's your 20 and your 26 MPa, and then again you end up with ended up with a negative answer, so I've done something quite wrong, and my angle is not quite the answer. I went over my solutions a few times, I'm not sure where I went wrong. That's not the correct answer, but the same method, just simultaneously solving these equations to try and find out friction and Coulomb. Now that we've done that, we need to consider the scaling effects. So we've done this part of the question, and they ask us how the value change of scale effects are considered. We have 5 meter and 27 meter joint length, so we need to change our JCS and JCR so it matches 5 and 27 meters. JCS and JCR that are given in the question, so like 16 and 96, they're based on a standard sample size, which is 100 millimeters. So you need to take it away, scale it from that 100 millimeter up to our 5 and 27 meter lengths. So that's the formula I'm using for JRC, sorry. And we're going to convert it we'll find out what our JRC for 5 meters is. Plug the numbers in, you get 4.5. Do the same for JCS up here. You end up with 13.2. So we've got our new JCS and JRC. That was just the small sliding mass. So we do the large sliding mass as well. So large sliding mass 27 metres, JRC 27 2.55, JCS 27 metres 5.62. Just be careful with the indice in the JCS equation. It's JCR, not JCS. I made that mistake a few times. So you get your JCR, JCS for the small and large. Then after that, you need to redo the whole question again with the new JCR, JCS. So just like we did in the first part of the question, we use the Barton equation to find out what the shear stress corresponding to the normal stress is. Normal stress stayed the same, like a 1, 1.4, 1.8. However, we have new JCR and JRC and JCS, so you get different answers. So I've recalculated them here, summarised them in the table here. So you get those new parameters. Again, just like we did before, we're now going to find the Coulomb parameters, so our cohesion and friction angle based on this new shear stress. Do that for the small sliding mass. I did my simultaneous equations, ended up with 30.96 degrees and 80 kPa. Again, not the right answer, but it's similar. A similar number of significant figures to the correct answer. Not sure where I went wrong again. Do the same for the large sliding mass. End up with 25.8 degrees and 830 kPa. And I've just summarised all my answers in that table here. So yeah, quite a long question, quite repetitive. But essentially the only formulas you need are like Barton equation, JCS conversion, JRC conversion, and the simple one we all know, Coulomb. I hope that was helpful.